Previously, we studied definitions that we use to study underdamped systems, so overshoot, rise time, and settling time. We saw the equation that defines percentage overshoot. Now, we want to see how to find them if we have the parameters of a second order system, like percentage, like damping ratio, C, or undamped natural frequency, or damped natural frequency. So these are the equations that give us the value. So for peak time, it's pi divided by omega d, or as we have omega d, we can write it as pi divided by omega n times square root of 1 minus c squared. Percentage overshoot is this equation. Obviously, you can substitute square root of 1 minus c squared with something based on omega d and omega n. But it is important to notice that equation 9, percentage overshoot, which we have provided 3 ways of writing it, could be only written if you have the damping ratio. Again, if you have the damping ratio, you don't even need omega d or omega n. If you have damping ratio, you can find percentage overshoot. So the percentage overshoot, the amount that you pass your final value, only depends on the damping ratio. And then for settling time is 4 times 1 over c omega n. Find k for the system with transfer function below, so that the system has critically damped response. What was critically damped response? Critically damped response was when c is 1. So find k such that, or so that, the system has c equals to 1. So the first step, we write the system as in standard format. Then this is going to be 2c omega n. This is going to be omega n squared, right? And c is supposed to be 1. So if this is 2c omega n, I substitute c equals to 1. Therefore, omega n is 1 plus 2k divided by 2 plus k. So now I'm going to have 2 equations. One of them is omega n written in terms of k. Second one is omega n squared written in terms of k. So I can square this equation and then put this equal to that. Now I'm going to have an equation which has k in both sides. And value of k can be found from solving this. Okay, now let's see how MATLAB deals with second order systems. Previously we studied how to compute step response of systems. It's just step command. Now we study another command, which is step info. If I use step info, MATLAB is going to return a lot of information about the behavior of my system. So let's say I have the system. If I define it and then apply step info, MATLAB is going to give me all the information that I need. Rise time, settling time, overshoot percentage, peak time, all these information that I care about, which are important for a second order system. Okay. Now we want to study what happens if we change the location of poles. So look at this figure, okay? So let's say we have an underdamped system. So it has 2 poles located here and here at negative c omega n plus j omega n square root of 1 minus c squared, and then the complex conjugate So it's a complex conjugate pair, right? So we are going to have negative c omega and negative j omega n square root of 1 minus c squared here. Now, let's pay attention to how big this vector that is connecting the origin to my pole is. Let's call that r. And then let's call this angle between the vector r and the real axis beta. Okay? Let's find the cosine of angle beta, and let's find out how big that r is. Since my pole is negative c omega n plus j omega n square root of 1 minus c squared, and that's this r, I can say, well, r squared is this thing squared plus this thing squared, right? Because this is a 90 degrees angle. So r squared is this squared plus this squared. What's this thing here? Well, the pole is negative c omega n plus j omega n square root of 1 minus c squared. So this is negative c omega n, and this is omega n square root of 1 minus c squared. Therefore, r squared is the first term squared plus the second term squared. Right? So if I simplify, this is going to be c squared omega n squared, and this is going to be omega n squared 1 minus c squared. If I add them up, I'm just going to have omega n squared. So r squared is omega n squared, therefore r is omega n. Wow, so this vector, the magnitude of it is omega n. Okay, how about beta? What is beta? Well, let's find cosine of this angle. Cosine of an angle is the ratio of this edge to r. What was this edge again? It's c omega n. So cosine of beta is the ratio of c omega n divided by r. But wait a second, r is omega n. So cosine of beta is c omega n divided by omega n, which is just c. So beta, this angle is arc cosine of c. Okay, so I have omega n and c both shown in a figure. So graphically now I know what's the meaning of damping ratio and omega n on the zero pole plot. Notice that in equation 12, c determines the angle that the vector makes with the real axis in the s-plane. In other words, second order systems, G1 and G2, which have different transfer functions, will have poles that are located along the same vector in case the value of c for both of them is identical. What does that mean? If I have a bunch of different systems and their poles are here, 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 and here, so they have different poles, but all the poles seems to be along the vector, the same vector. Obviously, they're going to have the same angle beta, and remember, angle beta was what? The cosine of it is c. So although these systems are different, their response is different, seems that their damping ratio is the same because the cosine is of this angle is going to be the same. And look at their response to a unit step. They have different responses, but what is common between them? Well, percentage overshoot. They have the same exact percentage overshoot despite having different responses. And we could tell that, we could predict that because they have the same C or damping ratio. Now, what if we fix the undamped natural frequency, or omega n? Well, if omega n is the same, remember omega n was the length of that vector r. So systems that have the same omega n but have different damping ratio are going to have their poles located on a circle because the radius is going to be constant, but their damping ratio is going to be different. Now, what does that mean for unit step response? Look at here. What do these systems have in common? They don't have damping ratio in common, do they? No, the damping ratio is different. Do these systems have the same frequency? No, they don't have the same frequency. So despite their omega n, the undamped natural frequency is the same. The frequency you are going to see, you're going to observe, is not the same. Why? Because this frequency of oscillations is omega d. It's not omega n. It's the damped natural frequency. Omega n is the frequency of oscillations if you didn't have damping. We do have damping, therefore these responses don't look alike at all. What if we fix the value of damped natural frequency, or omega d? Well, omega d is this. So if I have systems that have the same damped natural frequency, their poles are going to move horizontally because this is omega d. They're going to have different omega n and c. They are going to have identical omega d, which means their poles are going to move horizontally. In the time response of them is going to look like this to a unit step. Look, these systems are the ones that have the same frequency of oscillation. See, they all get to the peak at the same time, and then to the opposite peak at the same exact time. They have the same frequency of oscillations. Okay, how about alpha, fixed value of alpha? Equation 7 that we had before tells us what alpha is. Alpha is where, or basically the value of the horizontal value of my poles. So if different systems have the same alpha, despite having different damping ratio, their poles are going to move vertically. Now, what is common in their time response? They seem to have different frequency of oscillations. They seem to also have different damping ratio, or overshoot percentage. So what do they have in common? Their time response, their step responses behavior has the same envelope, right? They have the same envelope. Okay. So click on this link to see a visualization. It's very amusing in my opinion. Animation that shows how changing parameters would change the step response of the system. And let's see a few examples. Consider the system below. We want to find percentage overshoot, settling time, and peak time for a unit step. Is this written in standard format? Yes. So, because it's written in standard format, we can find omega n and c from the equation, and therefore using the equations, we can just substitute in and have TS, or settling time, TP, or peak time, and percentage overshoot computed. Please try to solve this without looking at the responses or the answer, and then check with the video.